Thank you very much. It's good to be back. Unfortunately, I have to be remote. I wish I could be there in Pullman, but my travel schedule dictates that I'm there next week, not this week. It's unfortunate, but we'll deal with it remotely. Yes, I'm actually a WC grad. I graduated in 2004 with my computer engineering degree, in 2007 with my MBA, both from Washington State. And at SEL, I've been in the realm of cybersecurity since I started there in 2008. I've done application engineering work, supporting our products for customers. I've done teaching, industry education. I have done product management, and now I'm in charge of the product development team for our security products. There's a lot we can cover in the realm of cybersecurity and industrial control systems. I'm trying to cover a lot of it very broadly, so we're not going to go super deep into any specific topic. But if there's interest in one of these topics that we hit, please don't hesitate to ask. I'd like to go as deep as you all would like to go. Today, we have 4 learning objectives that I think we'll try to hit with this presentation. First of all, learn some of the basics of industrial control systems with respect to cybersecurity. Understand the goals of cybersecurity for industrial control systems. Introduce energy system cybersecurity driving factors. Why are we doing it? And discuss some of the current trends and solutions. To get through all those learning objectives, we're going to go through this risk management model. And this is a model that was developed by the Department of Energy, I don't know, probably back in 2005, 2006, and it's been used as part of the DOE roadmap since. Even though it's got some age on it, it has proven effective. People still use it, and it's a great way to discuss risk management in industrial control systems. First thing you'll notice is there's 6 big blue boxes. I'm going from left to right. Setting security goals, identifying assets, systems, networks, and functions, assessing risks, prioritizing, implementing your protective programs, and then measuring effectiveness. After that, you'll notice there's kind of black arrows going backwards and feeding back into previous steps. And what that represents is risk management is really an ongoing process. We're never done. You can't go through it once and say, hey, I'm done, and be done with it, right? You're constantly learning, you're constantly relearning, the world is constantly changing, attackers are changing, attackers' mindsets and motivations are changing, attackers' techniques are changing, technology itself is changing without respect to the attackers. The world stage is changing, right? And so 10 years ago, we didn't really need to think too much about cyber war. Yes, it was a theory, but now it's actually happening in Ukraine. So I mean, that's just one current example of how the world has changed since I've started in this industry. And then finally, you'll notice on the left side there's 3 lines: physical, cyber, and human. Those represent kind of the vectors we need to think about for respect to risk management, right? You have to think about physical assets and physical security. You can't just focus on cyber because if someone does gain physical access to your system, all of the cyber efforts you've put in are probably useless. So you got to think about physical as well as cyber, but then there's the human aspect as well. Security is really a human problem more than anything else. If we think about an industrial control system and machines and building them to have quality and be reliable, right? Reliability is all about building a machine to operate the way it's supposed to operate. Security then is making sure that machine still operates in the face of humans who make mistakes and who may have malicious intent, right? So it's still an aspect of reliability. So we'll go through this whole model and hopefully get through those learning objectives. So first, we want to set security goals. Security goals should always line up with the business objective with the organization's objectives, right? You can say, hey, we want to be secure and just leave it at that, but that really doesn't give the defense team a whole lot of guidelines on exactly what's appropriate, how to proceed, where do we want to focus our efforts. There's not a whole lot there. So we always want to have security goals line up with those business goals. In general, our goal as defenders is we want to reduce the probability of a successful attack campaign that is material to the business organization or system, where material means it has a major impact on financial, economic, reputation, or legal aspects of an organization, right? You'll notice The goal here is to reduce probability. It's not to prevent an attack. It's not to stop attacks. It's not even to have 100% success of attack reduction or deterrence, right? The idea is to reduce the probability. We know attacks are going to happen. Attacks are always going to cost us money, even if it's in the form of, hey, I bought a new firewall or I put this new defensive measure in place, right? It's still going to cost us money. We're still going to be attacked. The reason we have to buy that firewall is because attacks will happen. So attacks will always cost us money. But we want to make sure that those attacks do not cause a loss of our ability to sustain ourselves as an organization or a loss of ability to serve our customers. Right? And that's really primarily what defense is in the industrial control system world, is make sure we can still operate. With that in mind, that really starts to dictate some of the things that we're going to talk about in the future of this presentation. I'm not going to go too much deeper into it right now. Second step here is to identify assets, systems, networks, and functions in industrial control systems. So I know most of you, if any of you are not experts on industrial control systems, so we'll spend a bit of time here. But in short, industrial control systems are all around us, right? Planes, trains, automobiles, gas and oil pipelines, refineries, electricity plants, food processing plants. They're everywhere, right? You can't go down the street without seeing an industrial control system. The stoplights at the local corner, right? Those are industrial control systems. Even something as simple as your coffee pot is an industrial control system. What makes an industrial control system not an information system is an information system deals with data. An industrial control system deals with the real world. Right, we're reading inputs from the real world and we're triggering outputs to modify the real world. Right, so in a car, for example, you have it's based upon CAN bus, or Content Automation Network Bus, and that Controller Automation Network Bus. And that CAN bus helps all of the ECUs in your car talk to each other, right? So it's monitoring your speed and changing your speed with respect to changing the throttle with respect to your speed to slow you up or speed you down in the case of your cruise control system, right? Or more modern cars have much better safety features, right? So they may have radars in them where it'll detect how close you are to the car in front of you, how fast you're going, and automatically hit the brakes for you to reduce the impact of the collision, right? So with that aspect, you can actually go back and look at the goals of ICS systems as well and say, okay, the goal with the automated braking was not to prevent the accident, but it was to reduce the severity of the accident, right? And make sure people can walk away alive. But they are everywhere. They are growing in numbers, and you cannot operate a day in the modern world without interacting with an industrial control system at some level. Very simple control system, which we are all probably familiar with in our houses or our apartments or even the classrooms, is your HVAC system, right? You've got an input, your temperature sensor, your thermometer. It's looking at the temperature of the air in the room. And then you have a thermostat, something that takes that input and does some logic on it and performs an output. In this case, it's saying, okay, the temperature is looks like 100 degrees. That's above my threshold of 72. So I'm going to trigger the HVAC system to turn on the AC to bring the temperature down. All right, so it's going to have its input and it's going to have some logic saying, okay, I want my temperature to be between, 70 and 72 degrees. Right, and if the input temperature is ever outside of that range, I'm going to trigger the furnace or the AC to bring us back into that range. Right, very simple control system, something we're all familiar with. To get a little bit more into what SEL does, deals primarily with electric power. You might be familiar with the circuit breaker, the fuse box in your house. Circuit breaker is a very simple analog control system, where each of these breakers in the panel monitors the current that's going through it. And it does this in an electromechanical fashion. And if the current exceeds its rated threshold, for example, 15 amps or 20 amps, then the breaker will trip, opening the circuit, making sure that we don't burn the house down, we don't electrocute somebody, we stay safe, right? Very simple. No, it is a control system in that it reads an input, the current flow, and triggers an output. It opens the circuit. But it's only a one-way control system. It can't go back and forth. If we scale this up beyond a house, we start looking at the bulk electric system. And this is where SEL products come into play. Right? It's the same concept as that circuit breaker in your house, but it's scaled up. Instead of looking at 120 volts and 15 amps, we're looking at 500,000 volts. What we're doing with our relays is we're looking at voltages and we're looking at currents on the line, detecting when things go out of bounds. So if current spikes above a preset threshold or voltage drops below a preset threshold, then we'll take an action such as trip a circuit breaker. And we don't have the circuit breaker built into us. We're more like the HVAC example where we're the thermostat, right? And we're recognizing what's happening on the electric system and triggering something else to take the output action, right? In this case, it's a circuit breaker. If we don't trip a circuit breaker in a fault condition, somebody could lose a life, somebody could get hurt. The transmission lines could heat up to a point where they actually melt and lose integrity. And if that happens, then widespread power outages, right? And so we're not necessarily designed to keep the power on. We are designed to keep the power grid safe. So faults then, this is what relays are detecting as faults. There's a lot of different types of faults. There's asymmetric, so your power grid is generally three phases, A phase, B phase, and C phase. And an asymmetric fault will happen on one or two phases, but not all three generally. So you can have phase-to-phase fault, which is this picture here, where we have a fault between those two phases and it causes a huge rush of current from one phase to another. We can have a phase to ground fault, say a transmission line, pole drops and a line lands on the ground, you have a phase to ground fault. You can have an arcing inline fault, maybe our line has failed integrity and starts to arc across it, but still in series. These are the types of things that relays nowadays try to detect. And it is critically important because if faults occur, then people can lose their lives in the ultimate scenario. So because of the criticality of that, a lot of effort's gone into relays over the years. Now, the oldest picture of a relay I could find was this Westinghouse relay from 1902. Right? The power system predates that, but this is the oldest picture of a relay I could find. The relay has evolved from 1902 to, well, now we're 2023, but our most recent technology that SEL produced came out in 2021. In 1902, they were known as electromechanical relays, very similar technology to what is in the circuit breaker in your house. Basically, it's got a disk, and as it rotates a little bit with respect to how much current is going through it. And if enough current goes through, it's going to rotate far enough where the circuit actually opens. And very simple, but very effective technology. And as you can see, it's been in use from the initiation of the bulk electric system up until 1984, when the very first microprocessor-based relay was produced. So before 1984, there was absolutely zero concern for cybersecurity in the power system because everything was purely electromechanical. Physical security was a concern, but there was no logic, there was no code, there was no communications. Everything was done right there in one box, very simple boxes. In 1984, with the first microprocessor-based relay, the industry found some huge benefits, right? Prior to that, with the electromechanicals, it would know if there was a fault and it would trip if there was a fault. But if that relay is on a 100-kilometer line, someone's going to have to walk that full 100 kilometers to figure out where the fault was. And hopefully they can find signs to really easily identify where it was. In 1984, since we moved to microprocessor, we can look at the harmonics on the line, we can look at the frequencies, we can look at everything that's going on with the waves, voltages and currents, and do some fancy math to figure out that, oh, this fault on this 100-kilometer line occurred about 10% down the line, right? And so you don't have to walk the full 100 kilometers. You can look, 10 kilometers down the line and say, okay, this is where the fault was, and then really narrow your search. And what this does is drastically speed up the time to clear faults and restore power for customers. So huge benefits there. Another benefit is now we can get data out of the relay. Prior to this, a relay was just a relay and it tripped or it didn't. But now we have sequence of event recorders. And so we know what happens. We can get some oscillography. We can say, okay, this happened at this point in time. And we can start to reconstruct events, which helps us improve the stability of the power system. Now, move to 2021, which is more modern, right? This is one of the latest relays we produced. The big differences between the 1984 model and the 2021 model are speed and communications. Back in 1984, the communications was on a parallel port. And so you could plug in your terminal to it and configure it and get information out. That was about it. In 2021, we have serial, we have Ethernet, we have copper, we have fiber, we have radios, we have dozens of communications protocols, all for different purposes. We have relay to human interactions, relay to monitoring system, relay to relay. It's a much more complicated beast than in 1984. And the reason I'm bringing this up is to show you the cybersecurity challenges that are in these devices that have progressed over time. 1902, none. 1984, minimal. 2021, now, if somebody were to stick a relay on the internet, which they could do, then it could be remotely attacked from anywhere in the world. Hopefully you don't do that, but if someone were to do so, it could be attacked from anywhere in the world. To give a little look at the operator's perspective, this is a control center, and you can see this big wall in the background. Each of those lines is a power line. Each of those dots and labels is a relay or a breaker or a transformer or some component of the grid. Back in 1984 and prior, if you were to have a power outage, you would have to call the power company for them to know about it, for them to be able to come out and start looking at how to restore it. Now with SCADA technology, SCADA stands for System Control and Data Acquisition. The operators generally know before anybody has the chance to call them that their power's out, right? And this doesn't exist everywhere, but in most places in the modern world, in the US in particular, almost all control or power systems are monitored by SCADA now. So this kind of demonstrates the communications requirements of the system, right? To have real-time knowledge of every state of your power system does require a lot of communications, a lot of awareness, a lot of uptime. One of the challenges of making this SCADA system work, though, is in ICS communications itself. So again, going back to the first relay in 1902 to actually well, we'll go back even farther than that. The birth of the bulk electric system can be considered to be in Folsom, California in 1895, when the first AC generation plant came online for long distance transmission. Right? Before that, everything was relatively short haul. Most of it was even DC. But the bulk electric system you can consider coming into being in 1895. Right? From there to 1984, and then 1984 to now are really the two big differences in capabilities of the systems. Even if we look at it from 1984 on, when communication started to become a factor, any communications technology you can think of between then and now exists on the grid now, right? The bulk electric system is so large that we cannot do a forklift upgrade of any part of it, right? It's really an evolution, a migration to more modern technologies. So those electric mechanical relays, even though they were replaced by microprocessor based in 1984, they're still, I think it's roughly 40% of the US grid is still controlled by by electromechanical relays, just because there's so much out there, it takes so long to replace. As we're moving more towards the modern stuff, we need more communications, right? People wanted communications in 1984. So what did they have as far as technology goes at the time? They had plain old telephone system dial-up. They had serial, they had frame relay, right? Moving on later in the 80s, they had SONUS and SGH and lease lines. Moving on later, we finally started to see some Ethernet pop up, right? Because the system never gets upgraded, I can guarantee you that every single one of these technologies is in use just in Washington State, right? Let alone the entire US, just in Washington State, all of these communication technologies are in use, in many cases, in the same system. right? So as it gets modernized in the 80s, right, they'll put in serial and frame relay. Then they build a new substation in the 90s, they'll put in Ethernet or Sonnet. Then they build a new substation in the 2000s, they might put in satellite or cell. Right, and so as the system evolves, you will have a communications channel that hits multiples of these types of communications, serial and frame relay and Sonnet and Ethernet and satellite, right, will be in one communications channel. And that makes it a very challenging environment for security because we're dealing with so many different legacy and modern technologies. Makes it really interesting to try to secure some of these systems, is just being aware of what is involved in building them. In general, when we talk about technologies in industrial control systems, there's two sides of technologies that we think about: information and operations. Information technology, you're all familiar with. It's very data-driven. It's what you use to talk to the internet, to talk to your bank, et cetera, et cetera. Operations technology is very machine-driven, right? It is primarily machine-to-machine, whereas information is trying to have us ingest information. Operations is having a machine talk to a machine to monitor or modify the physical world. And to compare and contrast the two sides, IT is a very dynamic environment. If I come in and sit down at my desk for the day and open up my email, I don't know what I'm going to see. I don't know if I'm going to have to go to one website or another one. I don't know if I'm going to have to send email to Canada or Mexico or China. I just don't know what's going to go on until I get set for that day, right? Whereas in operations technology environment, they're very static. You build a system, you commission it, you put it into place, you put it into production, you enable it, and then you don't touch it, period. You know exactly what communication is going to go where, you know who all the big talkers are, who all the big listeners are, who's going to take what actions. You've designed it, and it's going to do what you designed it to do. In IT, the tech should last from 3 to 5 years. At SEO, we have a policy of don't replace your laptop or your cell phone for 3 years. If it can last longer, great, but don't replace it for at least 3 years, right? In the OT environment, we have a tech lifespan of 10 to 60 years. We say 10 years because that's kind of the minimum expectation for any product to last. But I do have customers who tell me that they have a replacement cycle of 60 years. If something doesn't fail, they don't intend to replace it until it's been in the field for 60 years. Vast difference in OT versus IT. Makes a lot of challenges out there for doing things like updates and vulnerability management, right? Because if you're dealing with vulnerabilities for 3 years in the product, okay, that's feasible. But dealing with vulnerabilities and trying to maintain and update them for 60 years becomes much more problematic. In IT, it's kind of a best attempt world. And my favorite way to describe best attempt is looking at something like the SMTP standard. SMTP is the simple mail transfer protocol. It's how you send email from one person to another. The current SMTP standard dictates that you will continue to retry to send emails for up to 7 days. Right, so if you send it and fail, well, we'll wait a small period of time, then attempt again, until 7 days have elapsed, and then it just gives up, right? That's the best attempt. If it doesn't go through, it doesn't matter. 7 days is fine for that. In operations technology, we're very failure intolerant. What that means is if a trip command doesn't go from a relay to the breaker in the correct amount of time, say a millisecond, then that could mean the difference between someone walking away from an incident and someone not walking away from it. We have a very short lifespan on the data. We have a very high need for that data to go through. We cannot say, okay, I'm going to send it and hope it gets there. It absolutely has to get there. Because of that, you see a lot of redundancy in OT environments. You'll have a primary relay and a secondary relay doing almost the exact same function. They'll be monitoring the same lines, maybe have slightly different settings, but it'll be connected to the same breakers to make sure that things get triggered appropriately. If primary relay fails, then the secondary relay will take up the slack, right? But it's not just relays, it's for communications as well. We're getting to a state where we're commonly seeing the need for a protocol called PRP. PRP stands for Parallel Redundancy Protocol. And instead of having one network, you have two networks. You have network A and network B. And your relay will send communications out on both networks. And if there happens to be a failure in network A, then the should still go through on network B. And your receiving device will just respond to the first one, and the second one that it receives will drop, right? Because we're so intolerant of failures, everything has to get through in a timely manner. Because if it doesn't, it could result in the death of a person, which is not acceptable. So very failure intolerant. IT is data-driven, operations is machine-driven, I already mentioned that. And then IT is operates in very controlled environments, and operations is in uncontrolled environments. So with IT, I've got my laptop here on my desk in an air-conditioned room. I have a server in the data center that's air-conditioned and has fans and has filtered air, so it's a very clean environment. In the OT world, we'll have a relay sitting in a cabinet on a pole on the street. In IT, devices can exist and operate between 50 degrees and 90 degrees without a problem in an OT environment. I have equipment that has to operate in Nome, Alaska, as well as in the Saudi Arabian desert, right? So I have equipment that has to operate at minus 40 degrees C and 80 degrees C, which happens to be, I think, 172 F. So very different environment for the hardware equipment as well. So I hope that gave you a little bit of the idea of some of the assets, systems, networks, and functions that occur in industrial control systems. That'll help us better understand the rest of the risk management process and how to align those goals. So next we'll be hitting the assess risks portion of it. And to start with, we know what's risk. Well, as popularly got three components: threats and consequences and probability. Right, so your threat is what could happen. So for example, we have the Black Knight from Monty Python here. The threat is that someone walks up with a sword and stabs him or cuts him, right? So consequence is probably death. Probability is highly likely if it's a regular occurrence that someone walks around with a sword or doesn't like you or whatever it might be, right? We don't have a whole lot of control over the threat. And so we very often ignore the threat component. It is important to be aware of, but we don't have much control over it. We do have control over the consequence and the probability. So if you got the case of a sword, one way to protect yourself is to encase yourself in armor, just like the Black Knight did. What this does is two things, actually, is one, reduce the consequence, because a deadly blow without armor will probably result in a bruise with armor. Right, so you've reduced the consequence. And you can even say it will have reduced the probability in some cases, or change the probability in some cases as well, right? Because we're looking at the probability of not just an attack, but a successful attack. And if your scope is preventing death, then we probably reduce the probability. If the scope is reducing injury, then we probably have not reduced the probability, right? So it depends upon how you frame the risk itself and what armor does for you. But in short, we're trying to reduce consequence, and we're trying to reduce probability. Now, if you've seen Monty Python, you know that the armor didn't do the Black Knight much good. He still lost all of his limbs, still probably died ultimately. But in general, the idea is we want to reduce consequence where we can and reduce probability where we can. So to get into threats a little bit, Tim from the last presentation spoke a little bit about APTs and ransomware, so that fits nicely with this slide. In the ICS world, well, maybe more specifically in the critical infrastructure world, we generally talk about 4 levels of threat. Threat 0 is accidents, threat 1 is the garden variety, threat 2 is mercenaries, threat 3 is nation states. In the critical infrastructure world, the primary threat we are concerned with is nation states. Yes, mercenaries are a concern, garden variety, script kiddies are a concern, but the primary concern is nation states. Reason being is nation states, or APTs, if you remember from Tim's talk, the Advanced Persistent Threat, right? They have tremendous resources and they can work in general with impunity, right? Yes, they may cause something that will result in war, but short of causing war, they can do whatever they want and they don't have anybody to answer to, which is why they are such a big concern. They have huge resources and their goals are generally to get a leg up on anybody that they might eventually have a conflict with. Right? So they're not necessarily trying to start a conflict in most cases, but they're saying, hey, if we do get into a conflict, what can I do to improve my chances of coming out on top? Right? And one way is to get into critical infrastructure of their adversaries and stay there until needed. If we can protect against a nation state threat or an APT, then we can probably protect against mercenaries. In Tim's talk, he was speaking of ransomware, so that would be a mercenary type of an activity. We can almost definitely protect against script kiddies, those people, those attackers who are more curious than malicious and are trying to learn without realizing what their consequences are going to be. But then we also need to make sure we're talking about accidents as well. Right, protecting against a nation state is not going to necessarily protect against an internal, honest accident. It might, but it might not. So we do kind of need to consider nation state first and foremost, accident secondary, and then being aware of mercenary and guard and making sure the protective measures we put in place will also handle those. So that's kind of the vertical look at threats, threats 0 through 3. Looking at threats a little bit more horizontally, there's a lot of ways threats can come at us. Right, vulnerabilities. Vulnerabilities are bugs in systems that allow people to do things they shouldn't be able to do with computers or IEDs or relays. The vulnerability landscape, as you can probably imagine from the evolution of relays, the vulnerability landscape is changing as well. There's a lot more vulnerabilities that exist in relays now than there were in 1984, and that's still increasing. One way that's increasing is customers are constantly asking us to put in technologies to improve integration with their IT systems, such as putting lightweight directory access protocol or radius directly into a relay, so that a relay can interface directly with their Active Directory instance. Right, that adds more code to the relays, adds more complexity, adds more possibility for mistakes, both in configuration and in implementation. Right, so vulnerabilities are increasing. Communications are increasing, and so there's increasingly seen connections to untrusted networks, putting a relay directly on the internet. Now, most people will recognize, hey, this shouldn't be done, but there's a lot of people who either don't recognize that or aren't aware of the threats and don't care. So there's a tool called Shodan, which is effectively a search engine for devices. And you can go out there on the Shodan and search for SCL, Schweitzer, ABB devices and find devices connected directly to the internet. Now, in our experience, most of those are non-critical systems. Most of those are test systems. Some of those are demonstration systems. But you never know. One of those could actually be connected to a production system, and they have direct access to that production system now. The human factor is changing. People are becoming more aware, more comfortable with technologies, and in a lot of cases take riskier activities. Intrusions into the supply chain. Supply chain is becoming a major concern. One of the first instances of a supply chain attack I can remember was when I was in college, so probably 2002, 2003, where that's when digital picture frames were starting to hit the market. And there's a manufacturer in China who producing digital picture frames, sent them all out at Christmas time, and there were reports of this device coming from the factory with malware on it. And as soon as you plug it into your computer, now your computer's infected. Right, so that would be considered a supply chain attack, where something in the supply chain, something that you trust, is no longer trustworthy. There's a significant lack of detection capabilities. Again, I think Tim mentioned a lot about monitoring, and there's a lot of data out there, and there is. Most of the detection capabilities for cyber events exist more in the IT space and are tuned for the IT space, and they're not tuned or even capable of looking at a lot of the data that's in industrial control systems. That is something that is slowly changing. It's something that we at SCL are working on improving. But that is a threat as well. If we can't detect that somebody's there, then they can do more types of attacks. They can stick around longer. They can do more physical as well. And then there's becoming more demonstrated attacks. So Tim talked about a few of those. I'm going to talk about some of those as well. First one, highlighting the potential impact of an industrial control system attack. So this is a picture of the generation room at the Sayano-Shushenskaya Dam in Russia. And in 2009, they had an incident. And you can see there's, I don't know, 9, 10 generators in this room. And in the middle of each of those circles, you see that little cylinder sticking up. That's the top of the turbine of a generator. So the generator is actually the floor below. This is that pivot at the top. In 2009, this dam was under maintenance, and I can't remember which generator or generators it was, but it was one or two on the near side. We're under maintenance, and so they were in a locked position, and the inlet water from upstream from the reservoir stream was closed, so they could do maintenance on that generator. What happened? This was an accident type of threat, where the operator opened the inlet gate to the penstock, which lets the water into the generator, which then starts the generator spinning and sends it out. The operator opened this gate. Either it was the wrong gate that he mistakenly clicked on the HMI, or he didn't realize that this one was locked for maintenance or whatever. But from the computer system, from the control system, he did open the gate. And what that did was let a flood of water into the penstock. This water hit the locked generator, and can anybody guess what happened? Where's the water going to go if it doesn't have anywhere to go, right? The path of least resistance. It shot those generators straight up and out of the floor and into the ceiling. And those are 150-ton turbines. And the water completely destroyed this hydro facility in Russia, right? And that's one of those accident type of threats. And you can see there's a major impact here, right? This completely lost power for the entire region for quite a long period of time until they could rebuild and reroute, and cost probably billions of US dollars worth of damage. And I don't even know what the recovery time was, or if it's still recovered. I haven't done that follow-up, but it's just an example of the potential impact for industrial control systems. It is huge. I believe 21 people lost their lives in this incident. There were 21 people in the room when that happened. Fortunately, there was no downstream flooding. Fortunately, they were able to shut things off relatively quickly. But just seconds of that type of a flood is going to cause massive, catastrophic local damage. Some other examples of industrial control system incidents that have occurred over the years are Marucci Shire, Stuxnet, and Metcalf in Ukraine. I wasn't there for all of Tim, so I don't know how many of these he hit, but I know he mentioned Ukraine. Marucci Shire is one of the first incidents that I learned about. This happened back in the year 2000. Marucci Shire is a township in Australia, and one of their contractors, his name is Vitek Bowden, was fired. And the township failed to properly revoke his access credentials. And so he went around town with a couple of radios and his computer, hacked into, with his own credentials, hacked into the local sewage system and released close to 265,000 gallons of untreated sewage into streets, parks, rivers, et cetera, et cetera. So he made a huge mess. That kind of shows, the human aspect. The human had motivation to do harm because he was fired. He felt slighted. But it also shows that humans can make mistakes, right? If the mistake in this case was maybe it was a process that didn't exist, or maybe the procedure was not followed. But I mean, in general, you should revoke somebody's access credentials before you tell them they're fired, just to prevent this type of an incident. And I think he had the entire weekend where he was doing this before someone revoked his credentials. So fall down in policy and procedure there. Stuxnet occurred in, blanking on the year on this, I want to say 2010. Stuxnet was the virus that was put onto a USB drive. The USB drive was dropped into the parking lot of the Natanz nuclear plant in Iran. someone picked it up and stuck it into a computer. Again, kind of that human element, right? They needed a human to trigger the harm. What this did when it got on the system is it examined the system, and they know it examined the system because they've found Stuxnet in other computers around the world, but Stuxnet has not done anything malicious except in this one location, which means the attackers had knowledge of what was in this location, the systems that were there, the software that was installed, the specific models of centrifuges that were there. And Stuxnet, when it found that it was installed in the right spot, it did what's called a man-in-the-middle attack. It presented itself, it broke into the software, it broke into the control system, it embedded itself, and then presented to operators that everything is working nominally, while in fact it was causing all the centrifuges in the nuclear plant to run as fast as they possibly could, causing out of balance conditions and actually causing them to shake themselves apart. The estimate here, and since this is Iran, it's really hard to know. We can get this estimate from looking at satellite surveillance footage of trucks moving in and out, of stuff being replaced. But the low ball estimate for damage this caused was $243 billion US. The high ball is closer to $1 trillion. So that's a large spread, but even at the low end, you can see this was a massively expensive attack that someone performed against Iran. The third one on here is Metcalf. Metcalf is a substation in, actually it's a town, Metcalf, California, but there's a substation there where there was an attack, this was in 2013, I believe, where a gunman fired on 17 transformers and put holes in those transformers, caused them to leak oil, they leak their cooling fluid, and they eventually overheated and either burst into flame or just shut down. In conjunction with the gunshots, they also broke into an underground fault and specifically cut the fiber communications cables. So we can't just say it was a random guy with a gun shooting things. They actually did intentionally cause attacks, try to cause damage, and do something to prevent the operator's knowledge of these attacks. It resulted in about $15 million of damage. It did cost a little bit of power outages for people, but not substantially. We don't know the reason for this. We don't know who did it. There's a couple of theories out there. It could have been a resilience test carried out by the US government itself. They say that because it is a specifically targeted area, and they wanted to see what would happen in this kind of an instance, how the US could respond, how the operators could respond. It's also a low damage area, right? Anything happening in this area would have a fairly low spread impact to the surrounding community. Another of the theories, for the same reasons, is that was a dry run for a larger potential attack that a nation state would carry out in the future, right? See how the US would respond, see if it would be successful enough to carry out widespread. Right, so kind of shows why physical is important as well as cyber. And then the last one on here is Ukraine, and Tim mentioned Ukraine. In December 23rd, 2015 is kind of the start, maybe not the start, but when the first major blow had been sent to Ukraine from Russia. And Russia sent some emails to Ukraine, power company in the Ivano-Frankivsk region. And somebody opened it up, and of course it had malicious content, and they managed to break into their Active Directory instance. Poking through their Active Directory instance for a while, they managed to create themselves some accounts and backdoors, retain their access, and also found that this AD instance was attached directly to the industrial control system. And there were not proper firewalls or segregations in place. They were able to get to the power system HMIs, and start turning things off. In addition to this, they also started doing firmware uploads to routers, to firewalls, et cetera, to brick those devices so that the region would not be able to respond effectively or recover effectively. Well, the attackers kind of shot themselves in the foot because they did things out of order, and they killed their own communications before they had violated the entire system. So they actually self-isolated themselves, which was good for Ukraine. But this caused a loss of power for 6 hours to 1.4 million people, and is notable because this is the first time we know for sure an enemy nation state has used a cyber attack to cause physical damage. So those are actually five of the examples for why we talk about cybersecurity, right? We've talked a little bit about the physical piece of it. We've talked a little bit about the accidental piece of it. That's Stuxnet, Metcalfe, Ukraine. Those are all nation state levels, right? And that's why we put the focus there, because they can do a tremendous amount of damage. Once we've set our goals, we've identified our systems, we've assessed risks, then we can start prioritizing how we protect the system. And I'm not going to go a whole lot into prioritization because this is really an activity for the organization itself. There's not a whole lot of guidance, but there's some tools and tricks to help with prioritization. This is known as an Eisenhower matrix, where we're comparing urgency to importance. So in short, you classify all of your risks into, is it important and is it urgent? And if it falls into the important and urgent category, you do something to take care of it. If it is anything else, you probably ignore it, at least for now, right? And then once that important urgent category is empty, then you can look at the important not urgent stuff. And then the not important stuff you might never get to. Either defer it to somebody else, such as, for example, buying insurance, or outsourcing protection of that, or just, deferring it and never touching it if it's not important and not urgent. There's another type of matrix that some people sometimes use for prioritization. It's called the prioritization matrix. And instead of doing urgency versus import, it does effort versus impact, which is really good for like business decisions, but it's not quite as useful for cybersecurity decisions. Once you've prioritized, then you can start implementing your protective programs. We have a ton of defensive strategies we can talk about. Process, you always got to start with policies and procedures and processes. If you don't have a good policy, you don't have good goals, you don't have good direction for what is allowed in the business and what is desired by the business. But once we have that policy and those processes taken care of, then we start talking about some either technology specific or process specific things that we might think about. For example, reducing attack surface, right? Complexity is the enemy of security, right? We want to keep devices and software packages and everything we can as simple as possible. The more stuff we throw in there that's not necessary, the more likely it is we'll make a mistake in implementation, or the customer will make a mistake in configuration, or we'll increase the maintenance requirements because of vulnerabilities. Increased code means increased vulnerabilities, which means more updates. So reducing attack surface is one great strategy. Examining your system architecture and selecting the correct system architectures is crucial. Unfortunately, because of the way the industry grew, we have a lot of system architectures that are really not desirable from a cybersecurity perspective. There's a lot of companies out there that have flat layer 2 networks where everything's on the same broadcast domain, everything is accessible to everything else, no segregation. Right? That's really not a strong cybersecurity architecture from a networking standpoint. You really want to have something segregated, broken down to security zones and operational zones to make sure that once somebody gets in the system, they can't propagate through the system. Redundancy, we talked about redundancy for reliability's sake, but it's there for security's sake as well. And if we combine redundancy with data correlation, you can start talking about having a big brother tattling type scenario, right? I have 2 little kids, one's 4, one's 6, and I can hear in my head right now my daughter telling me, hey, Dad, Miles didn't put any toothpaste on his toothbrush, right? Just tattling about nothing important at all. But if you have redundant relays looking at the same inputs and looking at the same outputs, then you can have those relays tattle on each other, right? If somebody starts to misoperate for whatever reason, that could be an indication that somebody has messed with it. There's an attacker in it, or somebody has changed the configuration without authorization, or whatever the case may be, right? So if you've got the ability to have your machines tattle on each other, do so. It's a great source of information for how the system's going to act. Monitoring, Tim talked about monitoring, so I won't go too much into that. Automation, cryptography. Cryptography is one of those tools that can really benefit you or really harm you. Cryptography gets a lot of attention, and unfortunately, I hear a lot of the time, "Oh, just put some encryption in, and I'll take care of it." Right? But cryptography is not just encryption. Cryptography is protection of data, either from prying eyes, enhancing secrecy, or protecting data from violation. Looking at that integrity piece. And using it correctly in control systems is critical, because if you just start encrypting everything, like a lot of people tend to want to do, then you lose the ability to do the monitoring. You lose the ability to do the data correlation. You lose the ability of an intrusion detection or prevention system to do anything. Updates are very important. Access control is very important, as we saw with Marucci Shire. Training is critical. If the Russian at the power plant had better training, maybe that would have prevented that incident. There should have been technical controls in there to prevent it anyways, but maybe some additional training would have helped prevent that incident. And then look at physical. Right? It's not just putting in network firewalls or putting in cryptography. You have to think about the physical aspect. Motion detectors, cameras, light sensors, gates, locks, automatic doors, man traps, and all that stuff can help as well. And then backups. Tim also mentioned backups and how most companies don't feel like they have, or feel like their backups are better than they actually are. I'm going to second that. Almost no companies have adequate backups. And it's happened on more than one occasion where a customer asks me for their backup files, even though I'm just an application engineer doing support. Because they've had an incident where they've lost their configuration for a device. And so they go back to their vendor who did support for them at some point in the past to get a head start on recovering it. So backups are critical. If anything happens to your system, the best way to recover is to have good, solid backups. There's a lot of guidance for doing IT cybersecurity. Most of it comes from NIST and their special publication 800, which is very, very general. More specifically for electric systems, there's the NERC, Critical Infrastructure Protection Program. And for industrial control systems in general, there's a lot of stuff from ISA and IEC. So I won't go deeper into it, but if you're interested in digging, there's some places where you can go for more information. We're seeing a lot of reusing IT technologies and OT systems for protection. I've called out a few across the top here: TLS, X.509, LDAP, Radius, Syslog, and SNMP. They were built for the IT world, and they work very well in the IT world. They don't work quite as well in the OT world. People want them because, one, it's what they know, right? TLS encrypts everything on the internet. Therefore, it must be good enough for encrypting things inside an industrial control system network as well, right? That's the thought. One of the problems is TLS might be simple from a user perspective. It's not simple to implement. It's not even simple to create the standard, right? The standard has many iterations over the past 10 years. And if we're expecting a 60-year lifespan out of these products, how many more times is that standard going to iterate before the product is eventually dead? How many updates is that going to require for you to stay up to date with TLS? Probably a large number. But there's a lot of people that still want TLS directly in the relays. Again, need X.509 to do that, need to have some awareness of how these things work and the infrastructure around them. X.509 is not necessarily anything inherently bad with X.509 for OT systems. However, we see it being misused regularly. Right? An engineer who doesn't know IT, who doesn't know cryptography, who doesn't know X.509, often will go out and try to build an X.509 PKI system for their system. And I've seen multiple occasions where they have a problem with it. And so what they do is build it in such a way that they won't have to maintain it again. It won't need to be maintained again until after they've retired. So instead of using like 2-year or 5-year valid periods on their cert, they use 60-year periods, right? Make it somebody else's problem in the future because they can, right? So it's not that something's wrong with it necessarily, but it is misused. LDAP and Radius are often requested for user-based access control. Again, nothing inherently wrong with them, but they do add complexity to the system. They do add communications requirements, and they do propagate misuse of the system. If we look at the Ukraine attack, right? They got access to the industrial control system through Active Directory, through LDAP. That is fine, but to use it properly, you have to have separate AD systems. You've got to have your corporate system and a completely separate segregated OT system, right? Because when you attach it to email, when you attach it to the internet, when you do everything else, then the weaknesses that exist upstream can get propagated down. Same thing with Radius. Syslog and SNMPs, Syslog there's really nothing wrong with, but SNMP, it doesn't have the best access control. And fortunately, I don't see it being used quite as much anymore as had been requested about 5 years ago, but we still get requests for it. And that's mainly so they can use a single management system to manage everything. Right? They're familiar with their NMS. They want SNMP in our products to use the same NMS, which isn't necessarily a bad thing, but there are consequences, right? Engineering is trade-offs. You need to figure out which trade-offs to make and which to avoid. Additionally, just reusing a lot of this technology means we're adding complexity, we're adding attack surface, we're adding bugs, we're adding code to devices that have a very specific purpose, which inherently SEL disagrees with. However, not all IT technologies are bad. Some of them can be used as is, some of them can be used with a little bit of reinventing. Software-defined networking, for example, was developed at Stanford University and used heavily and popularized heavily by Facebook and Google for use of their data centers because it allows for a very incredibly dynamic network. Right? You spin up a new virtual server, you need a new virtual network to join it, to give comms to it. So SDN is great for that. However, SDN is also great for a really static environment that you'll find in ICS. Because we know all the traffic flows, we know which relay talks to which relay, we know which relays talk to the SCADA server, and we know it's not going to change because there's nothing dynamic in the system. We can pre-engineer all those flows and actually improve performance of the network and improve the security of the network, because if an attacker is not approved flow, they don't get to talk anywhere at all. Right? It's basically like having a firewall at every node in the system. So really powerful from a networking perspective there. IPsec, Internet Protocol Security, is cryptography that exists at layer 3 of the OSI model. It's really designed and intended for use across wide area networks, and it works great for that. If you're talking substation to substation or substation to control center, IPsec will work very, very well. But we can reinvent it a little bit and limit IPsec to those uses that work well. Right? We don't necessarily need road warrior type access. We don't need device-to-device access of IPsec. We can get rid of a lot of the complexity by limiting the types of interactions we allow it to have in the system. MACsec is similar to IPsec, except it operates at layer 2, the data link layer or the MAC layer. MACsec is a link layer cryptography protocol in the IT world where it encrypts from one switch to the next switch, which is amazing. We can adapt it for industrial control system world and actually have it provide end-to-end encryption on a local network. And when combined with SDN, becomes a very powerful networking security solution. MACsec is also nice because it is link to link. When and if we want to, we can use MACsec to do end-to-end encryption, but still be able to decrypt for an intrusion detection type of a system. Right, so that's starting to allow us to have the best of the crypto and the monitoring worlds. And then OAuth is in here because I mentioned in the last slide issues with LDAP and Radius and fitting those directly into the relays because it adds complexity. Well, OAuth is a wrapper protocol. And with something like OAuth, which if you're not familiar with what OAuth is, I'm assuming everybody is, but if you're not, OAuth is like when you go to a website and it says log in via Facebook or log in with your Google account, that's OAuth in use right there. With OAuth, we can offload the LDAP and the Radius and the TACACS and whatever other authentication protocol the customer wants, offload that to an upstream device. So if we put OAuth in all the relays, they can talk to an intermediary device, which then has the ability to talk to any or all of the proper authentication servers that might exist in the system. So IT is not all bad. There's a lot of things we can learn from it. But more than anything, we need to look at industrial control systems at a system level, right? So in this diagram, we've broken it up into 8 layers. layer 0 being physical, all the way up to layer 6 at the top of the thing. But then you also notice on the side, you have layer 7 people, recognizing that people interact with the system at every layer. We've further broken this down into below physical. It's an analog world. There's not a whole lot we can do there from a cybersecurity perspective. Above that is all digital. And then between layers 3 and 4, layer 3 down, we have M2M, that stands for machine to machine, where the vast majority of communications are between machines, from a relay to a relay or a relay to a PLC. And above that line is H2M, or human to machine, where humans start interacting with the system. Humans don't interact with the system for control for the most part. Humans interact with the system for the data that it provides. And so we can export the data into the SCADA or DMZ layer, and that's where humans will be doing most of their interactions. And so breaking it up into the system level, we can start to identify what security controls should go where, right? So the physical layer, cameras, motion detectors, that type of thing. And the protection level, not very much at all, because it is very protection and high speed focused, right? We want to have a dedicated job to do. We don't want to throw everything in that box. But at the automation and access levels, we can have more of those LDAP radius, crypto type technologies that where we can deal with the latency a little bit better. Finally, measuring effectiveness. We've learned a lot. You can learn a lot and feed it back into all your previous steps, right? Some of that is just reading and learning where attackers are at now, monitoring attacks that happen elsewhere, hopefully not to you, but then to test. It's really hard to come up with security metrics that says, hey, this thing I did created a 90% reduction in the impact to the organization, right? Because you don't necessarily know if that's true or not. There's no measures to determine if you've really been attacked, or if you've been attacked by somebody who is resilient, or if you're not even detecting it, that the attack has succeeded or not. It just hasn't caused you a loss yet. So it's really hard to build metrics on how successful your system is, but you can test with tabletops, with failure recovery exercises, with pen tests. There's other methods as well, but I do need to stress with the pen test, you never pen test on a live industrial control system. You don't know if you're going to accidentally take it down or not, right? So always test on digital twins or lab systems, never test on a production system. So ICS, cybersecurity, has unique considerations. We are not IT. We do have different goals. We do have different needs. We do have different environments. And that's something that's critical to be aware of if you want to work in the ICS cybersecurity space. You need to be aware of the applications. Is it and how critical those applications are? Maybe I should say that. Is it an application where you are providing power to a city of 10 million people? Or are you in an application where you're handling the temperature control in the building, right? They're vastly different with regard to goals, with regard to the needs, with regard to the level of exposure that you can accept. It's a very challenging environment for cybersecurity. There's things that I deal with on a day-to-day basis that are a year old, and things that I deal with on a day-to-day basis that are 30 years old. Right? So it's really fun in that regard, in that I don't know what challenge I'm going to have in a given day. But it is a challenge because I'm constantly learning and relearning about things that I knew and forgot, and things that I haven't yet come across, even if it's 25, 30 years old. And there's tremendous room for innovation. The industrial control system world is really in a fledgling state when it comes to cybersecurity. There's a lot of tools, regulations, et cetera, to try to improve that. But if you think about just something as simple as an update, right? With Microsoft, we have Patch Tuesday. Every first Tuesday of every month, you're going to get patches from Microsoft, right? And they can do that in a more or less entirely automated fashion because the communications is there, the expectations are there, the risk of a system going down is not that great for the most part. But in the ICS world, updates are very, very challenging. Doing a firmware update on a relay for some companies costs upward of $10,000 per relay. So just doing something simple like an update is a drastically different challenge in the ICS world from the IT world. So we have to think of different solutions, different mitigation measures that don't just say, hey, okay, update the firmware. So with that, I want to thank you very much for listening. I hope you enjoyed the presentation. And if you have any questions, I'm happy to take them.
Thank you very much, Nathan, for that excellent presentation. I'm going to see if there are any questions from the audience for you.
Everyone's hungry. It's lunchtime. I get it.
Right, it was so very clear. That's one of the ways to interpret it. Thank you very much again. We are going to break for lunch now. We appreciate it, and it's time.
Thank you very much. Have a good one.